In this movie, I'm going to tell you about a method to measure the behavior of a single ion channel. And that method is called patch clamping, and it was invented by these two gentlemen, Bert Sakmann and Erwin Neher. So the operation of the sodium channels, which were discussed in all the previous movies, is based on the voltage clamp recordings in the squid giant axon. And that recording, for example, is shown in the middle record here. And it shows the sodium current measured in the squid giant axon when the membrane potential was clamped at minus 10 millivolts when it was depolarized. And as soon as you depolarize it, notice you get an inward current, a downward deflection, and that automatically then shuts off. And the explanation for that was that the sodium channel, which is shown in the bottom, has both an activation gate and an inactivation gate. And the idea is that when the cell is depolarized, the activation gate opens, and that's responsible for the inward flow of sodium, the downward deflection of that current record. A moment later, the inactivation gate closes, and that's responsible for the turning off of the current. Of course, once you now repolarize the cell, make it negative again, you reset the gates. Although the behavior of individual channels, as I just described to you, was inferred from the voltage clamp records of the squid giant axon, no one had ever actually observed the operation of a single ion channel, and that's where patch clamping comes in. The basic method is to make an electrode from a piece of hollow glass, heat it, and pull it so that it tapers to a sharp tip that has a small opening. The tip of the electrode is then placed in the membrane or on the membrane of a neuron, as shown in this figure. The next step is to apply suction, so that a small piece of the membrane is actually sucked into the lumen of the electrode. The electrode is then pulled away from the neuron, taking with it a small segment of the membrane that contains a single ion channel. So now we have a patch of membrane with a single ion channel inserted into the lumen of the electrode. And there are a few important features of this arrangement that I'd like to point out to you. The first is that the membrane has to tightly adhere to the lumen of the electrode, forming what is known as a gigaohm seal. The significance of the tight seal is that currents cannot flow from the inside of the electrode around the membrane. Rather, the only current that can flow is through the ion channel when it opens. The second feature is that there is a wire in the electrode that allows the investigator to measure the membrane potential and to pass either positive or negative current. And the third feature is that the recordings are made in voltage clamp mode. This works in a similar way to the way that voltage clamp works in the squid giant axon that was explained in previous movies. In short, a brief current is passed through the electrode that immediately changes the charge across the membrane, thereby depolarizing that small patch of membrane in the lumen. That depolarization then causes the channel to open. When the channel opens, current flows through the channel and tries to change the charge across the membrane. The electrode then passes an equal amount of charge to prevent the membrane potential from changing, and that charge in this case is positive. It is the current that is passed by the electrode, which is equal to the charge flowing through the channel, that is measured. When the channel closes, no further current can flow through it, and no additional current is ejected by the electrode. In other words, the whole idea is to measure the charge or current that flows through the channel when the channel opens. Before describing the behavior of individual sodium channels, I need to present some nomenclature because it will make the description of the channel behavior easier to explain. The gates on a sodium channel can exist in 4 different configurations or states. The first is shown on the far left and is called the closed available state. It is called closed because the activation gate is closed and thus ions can't flow through the channel. It is called available because when the membrane is depolarized, the activation gate opens, thereby converting the channel from a closed into an open state. The open state, of course, is the second state that the channel can assume. After the channel opens, the inactivation gates close, causing the channel to assume a closed, unavailable state, the third state. It is called closed because the closing of the inactivation gate prevents current from flowing through the channel, and it is referred to as unavailable because depolarization will not open the channel. Remember that the inactivation gate is opened when the cell repolarizes, that is, when the membrane potential becomes negative on the inside. Thus, the channel is not available to conduct sodium ions with additional depolarization. The fourth state is also called closed unavailable, but here both the inactivation and activation gates are closed. I'll explain why this state occurs in a few moments. The state is unavailable because, like the previous unavailable state, depolarization will not open the inactivation gate, and thus the channel cannot conduct current even if the cell becomes depolarized. To make these states easier to visualize, I present them in different colors. The closed available state will be shown in gray, the open state in red, and both closed unavailable states in purple. And even to make things a little easier, I will simply refer to them as the available state, the open state, and the unavailable states. What patch clamp records showed is that the gates on a channel flicker and can assume any open or closed position. However, the probability that the gate will be in a particular position is strongly influenced by membrane potential. In other words, although the gates are likely to be in a particular position at a given membrane potential, say at rest, that position is not absolutely set. The idea that the positions of the gates on channels are probabilistic is one that students find awfully difficult to come to grips with. So let me give an illustration to make the point clearer. Let's consider the gates on one sodium channel, say at minus 70 millivolts, the resting potential. If we look at the gates at various points in time, what we see is the likelihood that the channel will have its activation gate closed and its inactivation gate open, as shown by the gray channels, is highly likely. The probability that the channel will be open, on the other hand, is very low, but it can happen, and it does happen. So next, let's see what the current response of a single sodium channel would be in a patch experiment conducted at minus 70 millivolts, the normal resting potential of a cell. This is a similar record to the one I just showed, except here we are also looking at the currents that flow through the channel when it's open. Keep your eye on the channel that's actually embedded in the electrode. The flat black line indicates no current flow, while the downward deflector shown in red indicates the flow of positively charged sodium ions through the open channel. There are three things I would like to point out. First, for the vast majority of time, the channels are in an available state as shown by the gray channels. Second, when the channel opens, it opens fast and it closes fast, thereby producing the rectangular shape of the open state of the sodium channel while the sodium current flows through it. Third, at two instances in time, the channel is in an unavailable state as shown by the two purple channels. In other words, the channel flickers and assumes various states, even at rest, but the channel is in an available state for all but a few moments in time. So our goal is to explain the sodium currents evoked in the squid giant axon as shown above, based on the probabilistic behavior of individual sodium channels in response to depolarization. So the next thing we have to do is in fact see how the sodium channels respond when the membrane is depolarized. Next, we're going to see how an individual sodium channel behaves when the membrane is depolarized. We start off at rest, that is minus 70 millivolts, and then inject current so that the membrane is strongly depolarized to minus 10 millivolts. The current is injected at the time point shown by the first arrow, and the membrane is brought back to rest at the time point indicated by the second arrow. Be sure to watch the sodium channels in the lumen of the electrode. Okay, here we go. Okay, the channel behaved in a way that we would have predicted. That is, it opened briefly when the membrane was first depolarized, and then inactivated quickly and remained inactivated for the duration of the depolarization. When the membrane reverted to its resting state, the channel reset and once again became available. Now, let's take the same channel and depolarize it again and see what happens. Here we go. This time, the channel behaved somewhat differently to the second depolarization. It opened quickly when the membrane was depolarized, but then turned off for a moment, and then opened a second time, but for a period that was twice as long as the first opening, as indicated by the red stretched channel. It then inactivated and was unavailable for the duration of the depolarization. Now, let's take the same channel and depolarize it a third time. Here we go. This time, the channel did not open at all, even though it was depolarized to minus 10 millivolts. Here's how the channel might have behaved 8 times, each time to the same depolarizing step of minus 10 millivolts. If we assume this channel is representative of all sodium channels, then this record could also be viewed as the responses of 8 different sodium channels when the membrane was depolarized to minus 10 millivolts. If these 8 sodium channels were neighbors that were clustered on a patch of axon, the total current on the patch would simply be the sum of the individual currents. The summation of the microscopic currents, the currents that flow through each sodium channel, is shown here. The summation of the microscopic currents, which is shown in the top record, has the same shape as the current record recorded from the squid giant axon, which is shown below and labeled as macroscopic current. The only difference is that the current from the squid giant axon is larger, because that current was generated by thousands of sodium channels. The conclusion is that the summation of the quirky behavior of individual sodium channels can fully account for the smooth sodium current that Hodgkin and Huxley recorded from the giant axon of the squid. The same applies to the behavior of potassium channels, but you can read about the potassium channels in the chapter on patch recordings. In the next movie, I will show how the probabilistic behavior of sodium channels can produce some surprising features that relate to the threshold for generating an action potential. Specifically, we will consider how the probabilistic behavior of the sodium channels can account for 2 strange phenomena: depolarization block and anode break excitation.